Chapter 14, number 33. A tuning fork vibrating at 512 Hz falls from rest and accelerates at 9.8 meters per second squared. How far below the point of release is the tuning fork when waves of frequency 485 Hz reach the release point? Okay, so for number 33, they tell you that it starts from rest, so your initial velocity is 0 meters per second. They tell you that your acceleration is 9.8 meters per second squared. The frequency of the source is 512 Hertz, and the frequency of the observer is 485 Hertz. Okay. The source is moving away from the stationary observer based on what they tell you in the problem. So because of that, I used this formula right here. Plugging in my values, I solved for the velocity of the source to be 19.1 meters per second. That's step one. Next, you need to see what the distance is before the object, before the tuning fork reaches the 19.1 meters per second. So before it changes the frequency. So that's what I did first. So I used the timeless equation because you don't know how long it took. And I used the 19.1 meters per second as the final velocity, 0 meters per second as your initial velocity. And I found that it took 18.6 meters, or it traveled 18.6 meters until it got to 19.1 meters per second. The next thing that I did was solved for how long it actually took to get to the observer. So for that, the velocity is 343 meters per second because we know that we are in air. We also know that it traveled 18.6 meters based on what we just solved for. And the time that it took to do that was 0.0542 seconds. If you rounded to 0.05, that's totally fine. I just left it with everything, with the entire answer. So the last step was to find out what is the additional distance that occurred during this time. And for that, I solved using the distance equation. So I used the distance equation, I used the time that it actually did take, in addition to the velocity that it started out with, because remember, this is the new speed, the distance that it fell at this speed. And I found that this took 1.05 meters. Adding those two distances together, you end up with a final total distance of 19.7 meters. Number 34, expectant parents are thrilled to hear their unborn baby's heartbeat, revealed by an ultrasonic motion detector. Suppose the fetus's ventricular wall moves in a simple harmonic motion with amplitude of 1.8 millimeters and frequency 115 beats per minute. The motion detector in contact with the mother's abdomen produces sound at precisely 2 megahertz, which travels through tissue at 1.5 kilometers per second. First, find the maximum linear speed of the heart wall. Okay, so first of all, they tell you the amplitude in millimeters, they tell you the frequency, beats per minute, and they also tell you the speed. Obviously, all of this is going to have to be converted. If you want to convert first, which is what you probably did, then by all means, go for it. You'll see that I converted throughout the problem. But if you wanted to do it first, definitely do that. The formula to solve given linear speed, my v, and the amplitude is this one right here. V equals omega times A, where omega is your angular frequency. So first thing that I did is I wanted to solve for what my angular frequency was. And based on chapter 13, we know this formula, omega equals 2 pi f. So plugging in 2 pi, you have to convert your frequency like we said. So 115 beats per minute, you need to convert to seconds. And if you do this correctly, you'll end up with your omega being 12.04 radians per second. Then all you need to do is plug into your equation, V equals omega A, where your omega is a 12.04 radians per second. Your amplitude, there are 10 to the negative 3 meters in 1 millimeter. Milli is 10 to the negative 3, so I converted this way. and I ended up with 2.16 times 10 to the negative 2 meters per second. For letter B, you want to find the maximum frequency at which sound arrives at the wall of the baby's heart. Okay, so for this is the Doppler effect. So we need to figure out what's moving, what's stationary, what's going on. So the heart wall is the moving observer. The detector that is going to be measuring is the stationary source. As you put the detector on the mother's stomach, the detector is not moving. What's moving is the heart wall inside. So I used this formula right here, coming right from your PowerPoint. And what I did was I converted your megahertz. So the 2 megahertz, mega is 10 to the 6. So I converted that first right over here. Plugging in with your values, I plugged in the kilometers per second, and this is my conversion here. I just took a shortcut and didn't do the putting it over 1 or anything like that. I just multiplied. Kilo is 10 to the third or 1,000, so I multiplied by 1,000 basically. And the 2.16 times 10 to the negative 2 meters per second is what we already solved for in part A. Plugging in here, we end up with our answer of the 2.000029 hertz. For letter C, find the maximum frequency at which reflected sound is received by the motion detector. By electronically listening for echoes at a frequency different than the broadcasting frequency, the motion detector can produce beeps of audible sound in synchrony with the fetal heartbeat. Okay, so again, you need to say what is going to be moving, what's not going to be moving. The heart wall is moving, the detector is not. So for this one, I used this formula right here where you subtract your speeds. I took the frequency that we found for part B, this one right here. I didn't I didn't put it in scientific notation. You definitely can, and I know that we do that all the time. But for my work, I wanted to make sure that I showed exactly the number that I did get so that you can match it with yours. If you did go and put it as 2 times 10 to the 1, 2, 3, 4, 5, 6 to the 6th, that would be fine also. The other thing that I would also say though, if you look at what your answers, the difference in your answers for B and C do vary based on the 29 and the 58. So for this, I know I always say like go to two significant digits. For this one, if you go to 2 significant digits, you're going to not see the difference between the values. So take it for what it is. If you go through and you're doing the problems and you see that there is a difference having multiple digits, then I would tend to probably just leave the digits that you have there. So solving for this, you end up with 2.0000458 hertz. For number 36, we have a yellow submarine, like the Beatles song, traveling horizontally at 11 meters per second using sonar with a frequency of 5.27 times 10 to the third hertz. A red submarine is in front of the yellow submarine and moving 3 meters per second relative to the water in the same direction. A crewman in the red submarine observes sound waves from the yellow submarine. Take the speed of sound in seawater as 1,533 meters per second. And letter A, write equation 14.12. So you had to go back and you needed to look in the chapter and see 14.12. So the first thing that I have here is all of the givens. I wrote it all out. I listed it as the velocities that they told you, the frequencies, all of that. For letter A, this is your general formula here. So I went back 14.12. This is your answer. For letter B, which submarine is the source of the sound? Okay, the yellow submarine has to be the source of your sound. Letter C, which submarine carries the observer? The red submarine carries the observer. You have to look at what your frequencies and your speeds are. So again, they tell you that the yellow submarine is traveling at 11 meters per second, having a certain frequency. The red submarine is moving at 3 meters per second relative to the water in the same direction. So you have to just make sure you're reading exactly what it tells you. So which one is the source of the sound? Which one is carrying the observer? That comes right from the question. For letter D, does the motion of the observer's submarine increase or decrease the time between the pressure maxima of the incoming sound waves? How does that affect the observed period and the observed frequency? Okay, so I said the motion of the observer away from the source tends to increase the time observed between arrivals of successive pressure maxima. This causes an increase in the observed period, which will be a decrease in observed frequency because, as you know, period and frequency are inverses of each other. T equals 1 over F, F equals 1 over T. You should know those formulas. For letter E, should the sign of V naught be positive or negative? Well, it should be negative to decrease the numerator and decrease the observed frequency. You have to make sure, here's your formula. So you have to, if you want to decrease the observed frequency, the numerator must be negative. Letter F, does the motion of the source submarine increase or decrease the time observed between the pressure maxima? How does this motion affect the observed period, the observed frequency? The motion of the source toward the observer tends to decrease the time between arrival of successive pressure maxima, which will decrease the observed period and obviously inversely increase the observed frequency. For letter G, what sign should be chosen for V of S, the velocity of the source? The velocity of the source should be positive to decrease the denominator, which increases the observed frequency. And again, all you need to do is look right back at this formula here. So if you have a positive V of S, then you're subtracting, which is therefore going to decrease your denominator. And lastly, letter F, substitute the appropriate numbers and obtain the frequency observed by the crewman on the red submarine. All right, so based on everything that we talked about as far as like A through G goes, using your letter A formula, plugging in the frequency they told you, using the seawater speed, and then making your velocity of the observed as well as the velocity of the source negative and positive, you end up with an answer of 5.3 times 10 to the third hertz.